Okay, today's lesson is about probabilities from tree diagrams. Now, you might have done tree diagrams in the past. Hopefully, this is just consolidating that, or if not, introducing it to you for the first time. So, the key thing is we're looking at equally likely outcomes. So, the problem I've got is for lunch, the hostels have a choice of a lunch they can choose. A sandwich, and that can be made up of Vegemite, jam, or ham. A drink is either orange juice or Sprite. A piece of fruit, which can be a banana or apple. So obviously we need to think about how many choices there are, and we have the questions on the right. If I choose at random, what is the probability that I would get a lunch that contains, first of all, a ham, orange juice, and a banana? So remember, in probability, the key thing is we want to know how many times is favourable, or what we're interested in, divided by the total, or the total number. So the first thing we need to do is work out what the total number is. So, and a probability tree helps us do that because it puts a series of events. We have 3 events that everybody's going to choose: a sandwich, a drink, and some fruit. And then we have to think within the choices of each one. So the first event, a sandwich, how many choices are there? That's right, there's 3. Okay, and they are Vegemite, jam, and ham. Obviously, I'm using the letters to save a bit of time. You've got to be careful a little bit about setting up your tree to give yourself enough space and make sure it all works. So the second event, there's a drink. So there's 2 choices, but that is for all 3 of the sandwiches. So for Vegemite, there's orange juice and Sprite. For jam, there's orange juice and Sprite. And also for ham, there's orange juice and Sprite. So we can put those letters in there as well. Now the last one is choosing the piece of fruit. Again, there's 2 choices, and we can label those as well. So going along each branch, so if we take a look at this branch, for example, what we end up with is Vegemite, orange juice, and an apple. This branch is the jam, Sprite, and an apple. So there are all the outcomes, and you can see there, if we count them up, there are 12 outcomes. So what that means is for all of our probabilities, they're going to be out of 12. So for our first question 1, we're looking for the favourable outcomes for ham. So in other words, ham, orange juice, and banana. So looking down our list, we can see that there is 1 ham, orange juice, and banana. So the probability is 1 out of 12. Looking at question 2. So looking at question 2, it's just asked us about Vegemite and an apple. So we're really looking for anything that has VA. All right. In this case, the drink doesn't matter. So what we end up with is V and A, VOA, and VSA. There's no other outcome looking at that contains Vegemite and an apple. So that means there are 2 favourable outcomes, so it's 2 out of 12, which we could, if we wanted to, simplify to 1 out of 6. Okay, looking at question 3. Okay, question 3, we're looking at no jam, but has orange juice. So that basically means we're looking for anything that is Vegemite and orange juice, and also ham and orange juice. So anything that's got VO or HO. So VO, VO, HO, HO. So in this case, it's 4 out of 12, which we can simplify to 1 over 3. And the last one is we're looking for Vegemite or an apple. So basically any one that contains a V or an A. Okay, so a V or an A, so we end up with VOA, VOB. So it doesn't matter that it doesn't have an A because it uses the word or. It would be different if we used the word and. So we've got V there, or an A. So this JOA doesn't have a V, but it does have an A. And we've got JSA, HOA, and HSA. So counting those up, we've got 1, 2, 3, 4, 5, 6, 7, 8. So 8 out of 12 is the probability that you'd get a lunch with Vegemite or an apple. So simplifying that, we end up with 2 over 3. So you can see when it's equally likely outcomes, everything has an equal chance of being selected in each one of the events. It's just a case of counting up the outcomes. It's slightly more trickier when we're looking at things where each event there's not an equal chance of happening. So let's take a look at this one. Peter and Becky run a race and play a tennis match. The probability that Peter wins a race is 0.4. So because in this event, the race, there are 2 outcomes, either Peter wins or Becky wins. 0.4 means that there's a greater chance that Becky's going to win. So if we actually look down at our tree diagram, you can see that we've already had Peter's probability put in. So what do you think the probability that Becky wins is? What would both of them have to add up to? That's right, it would have to add up to 1. And the reason for that is if the only outcomes is Peter winning or Becky winning, then that must be 100%. There's no other possibility. So it means it must be 0.6 for Becky winning. Now for the next part, the probability that Becky wins the tennis is 0.7. So again, because it's more than 0.5, it's more likely that Becky's going to win the tennis. So we have to write 0.7 in. Sorry, 0.3. And that's because 0.3 and 0.7 add up to 1 because they're the only outcome. Now looking at the branch at the bottom, has to be the same as well. So probability of Peter winning 3, probability of Becky winning 0.7. So now we've got our probability tree completed. The next thing we've been asked to do is what is the probability that Peter will win both events? Now that was really easy last time. We could just say it's 1 out of 4. That's assuming that the probability of Peter winning each one was the same as Becky, but it's not. So what we need to do is work out the probability of each outcome. And how we do that is using the AND rule. So the probability of Peter winning the race and winning the tennis is that we multiply. So it's 0.4 times 0.3, which gives us that answer. The probability that Peter wins the race but Becky wins the tennis is 0.28. The probability that Becky wins the race but Peter wins the tennis is 0.18, and the probability that Becky wins both is 0.42. So looking at those numbers, because this is the largest, the most likely outcome is Becky winning both of the tennis matches. Both the race and the tennis. The least likely outcome is Peter winning both. So the probability that Peter wins both is 0.12, and the probability that Becky loses the race but wins the tennis is 0.28. So this was an example of a probability tree where it didn't matter who won the first event, the second event, the probability was the same. So it didn't matter if Peter won the race, Becky would have the same probability of winning the tennis. That's called an independent event. So the running race and the tennis were different, were independent events. Their probabilities didn't affect each other. In this next example, we're going to look at something where there is a dependent event, that the second outcome is dependent on the first outcome. So Lucy has a box of 30 chocolates. 18 of them are milk chocolates and the rest are dark chocolate. She takes a chocolate at random from the box and eats it. And then she chooses a second. First part of the problem is draw a tree diagram that shows the possible outcomes. I actually want you on a sheet of paper, have a go at thinking about the two events and what they are, and then what the outcomes are. So have a go at drawing the probability tree, pause the video, get that done, and then come back. Okay, hopefully you've had a go at drawing the tree. This is what it should look like. Is you should have had the probability of milk and dark because they're the two outcomes, and then for the second pick it's the same. Now, because you were told at the start that there were 18 milk chocolates and 30 in total, that's why we ended up with a probability of 18 out of 30. Because it's 18, it means that there must have been 12 dark chocolates. Now, in the second pick, the key thing that you've been told is that she ate it. Lucy ate it. So that's going to change the numbers slightly. So rather than being out of 30 this time, it's out of 29 because one has been eaten. Now, because she chose a milk to start with, rather than there being 18, there are 17 in the container. But if we look at the dark chocolate, we end up with, we've still got the 12 because none of them have been eaten. However, if we go through the branch where if she eats the dark chocolate instead, you can see we stay with the 18 out of 29 for the milk because none of the milk have been eaten, or the 12. We end up with 11 for the dark. So what that means is it changes our probabilities. To work out the probabilities of all the outcomes, we multiply along the branches, which you can see by these calculations, and we get our answers. Now, some of these can be simplified a little bit further, but I'll explain why they've been left as they are if you just multiply them together. So the question we've got here is, I calculate the probability that Lucy chooses 2 milk. Okay, and that's the one for 2 milk. So the probability that Lucy chooses 2 milk is 306 over 870. Now the second question in part 2. A dark chocolate and a milk chocolate, what's the probability that Lucy chooses a dark chocolate and a milk chocolate? Well, she could either choose a milk chocolate first and then a dark second, which is this outcome, or she could choose a dark, then a milk, which is this answer. So what we have to do is we have to add them together. And this will illustrate the reason why you have to, it's a good idea to leave the same denominator if you can. So because it's 870, then I can go 216, sorry, because these fractions have the same denominator, I can just add them together as they are. I don't need to change them or anything like that. So it's 870 over, 216 plus 216 over 870, which adds to 432 over 870. And then that answers our question. So it also makes it a lot easier if you have the same denominator to compare. We can just compare the numerator, because they're the same denominators, we can compare the numerators, and we can see that the lowest chance is to get 2 dark, and the highest chance is for to get 2 milk. Okay, so this page is just summing up what we've sort of looked at. When you're using a probability tree, key thing is that the addition rule, the OR, is going downwards or upwards, and the multiplication rule is to work out the outcome along each branch. And you can use the word, if you use the word and, you should be doing multiply. If you use the word or, you should be adding. So go to your OneNote and have a go at